Let me say something more about this map morphism, that that if I take a closed subset, say Y, in V, say this is V of I, which is V of say F1, F2, Fr, is a closed subset here in An. Then this you have a map from An to Ui, right? This psi I. Okay, then you can talk about y, the Y is a subset, so you can talk about psi I of Y, which is here. But Ui is in Pn, and psi I of Y, this is a subset, Y is a closed subset. So if you assume for time being that this is isomorphism, then psi Iy is also a closed subset of Ui, but Ui is the open subset of Pn. So if you take the closure of psi I of Y, what it is? So the psi I of Y closure, this is nothing but V of you know that whenever you have a polynomial, you can homogenize, right? Homogenize the polynomial f1, f2 r. So this is an in the with respect to I, right? Yeah. So yeah, I'll explain. I'll write down what is it. So f1. So you remember that home I. So if An, if I write this is the variables as k, y1, y2, yn, then I can define a map, right? K of y1, y2, yn to k of x0, xn, right? If I take some polynomial f, then what I do, I take, suppose f is of degree d polynomial, then what I do, I take xi power d, suppose f is in Rd, so if I call this is R, Rd, so Rd means degree d polynomial, and it need not be homogeneous. So what you do, you multiply xi power d with you replace y1 with x0 by xi, and this is how you do, right? This is called homogenization process. And similarly, you have the other way around, that you have dehomogenization. Huh? You have to put at the other place xi, you put 1. So there is a other way you have defined. So this goes to homogeneous polynomial. If you take a polynomial f, then you can homogenize. Similarly, if you take a polynomial f, which is a homogeneous polynomial, you can just put f y1 1 yn. This need not be a homogeneous polynomial. At the ith place you put 1. This need not be a homogeneous polynomial, but it will go to less, it may be less, degree d less. So it will be something. So it's a, so let's write here r less than equal to d. So r less than equal to d means the polynomial of degree at most d. So this is the process, right? Dehomogenization and dehomogenization. So the point is that this psi I of y, if you take a closed subset in Pn, in An, so you want to know what is psi I or psi I of y, but psi I of y is just a copy of ui, but you want to know what is its closure. The closure will be a projective variety, and this is the projective variety, or not projective variety, algebraic subset. You don't know whether it is a prime ideal or not. Now the opposite question, that so this is a morphism. So if I take some y here, if I take some z, say z here, a closed subset, and if I intersect with ui, z intersection ui, what is the inverse image of psi under psi I? Understand? So, if I take a closed subset here, so closed subset of ui are basically closed subset of Pn intersect with ui. So, now if I consider z of I as z intersection ui, now what is psi I inverse of z? Zi. So, this is the dehomogenization. So, if z, so that's what the, so psi I of, so if, so suppose Z is in Pn closed subset, suppose Z is given by say V of F1, let us write capital F1, FL, then you consider Z intersection ui, and consider psi I inverse of Z intersection ui. So, this will be a closed subset in An, right? And what is that? This will be the zero set of dehomogenization of F1 the ideal generated by that. Right. So, example you see, so you take P2, so you have 3 coordinate x, y, z. Then you consider the consider U2. So, U2 is nothing but z not equal to 0, right. So, now you take the curve C inside A2 given by this y square equal to x cube plus x plus 1. Then psi 2 of C closure, what it will be? It will be the homogenization of this. So, what is the homogenization of this polynomial? It will be V of y square say x y z. So, y capital Y square z equal to x cube plus x z square plus z cube. Right. Okay. So, now let us in last 5 minutes let us recall the regular functions on in projective space. So, regular functions, because you see that I said that this is a isomorphism. This psi I is a isomorphism, but for quasi projective variety I should know what is a morphism. To define morphism, I have to define what is regular function, because that is how it is defined. It takes regular functions to regular functions. So, first let us talk about regular functions. So, I have already defined, but let us recall again. Regular functions on quasi projective. So, suppose y is quasi projective and P is a point in y. So, if P is a point, now you know this Pn, it can be covered by these standard open subsets which are isomorphic to copies of An, right. Pn you can write it as a union of ui's. Now this point P is in y. So, P is in some ui, right. So, suppose P is in it can be in another uj also. there's nothing to worry. Okay, but P is in some ui. Okay, now you suppose you have a function. Suppose f y to k is a function. The function. So then f is said to be regular at the point at p belongs to y if it satisfies one of the equivalent condition. So one condition is that if it satisfies the following equivalent condition. Either one of, and there two are equivalent, so either one of this. So one is that if when you think y intersection ui as a affine variety, so homeomorphism, right? Ui is a homeomorphism. So you think y intersection ui is regular at p in affine sense or quasi affine. So you know what is a regular function at for a affine variety, or there exists a V open subset in in Y, and P is in V, such that f restricted to V, you can write it as some f by g, where f and g are homogeneous in S, and g of V is not 0. So homogeneous in S of same degree. So then you say, so this condition, two conditions are equivalent. So this is one, either one of these. So one in the sense of for regular. So for a, now you say the function is regular if it is regular at every point. That's how you define that. You say that a function, so f is regular at y. So f is regular if it is regular at every point. That's how you define, right? So two way you can define for regular functions in the projective way. One in the, so you go to the affine case, there you say that locally it is a regular functions. Another way you can define that in the whole, in the coordinate ring level case, that you locally it should look like g mod h or f by g, but f and g are polynomials in n plus 1 variable. But when you write in the UI sense, then it is a n variable, right? When you go to the affine case, so this is the two way you can define your regular functions. Now you define your morphism between two quasi projective varieties. So if x y quasi projective, a map say f, again I am denoting by f. If f is continuous, so this is a topological space, and the second condition is that it takes regular functions as regular functions. So that means for all u open in Y, f hash, or what is the notation? F upper hash from OY u to OX of f inverse u. for all u and for all f. Sorry, f is not a good notation. Okay, let's write. Psi or phi. For all f belongs to OI of u. So this the set of all regular functions on y, this forms a K algebra. Sum of regular functions are regular, product of regular functions are regular. So this is called this forms a sheaf. For every open set U, you define set of all regular functions on U. So and that sheaf of regular functions. So this OI. So OI of U, you define it as the functions from U to K. F is regular on U. And this is a K algebra. If Y is defined over K, so this is a K algebra. And so this defines OI. So restriction of regular function again is a regular function, because if you take a if it is a regular function, then if you restrict to a smaller open set, so that gives a restriction map. So this is a sheaf of regular function. So this is called sheaf of regular function. So then what is so this is basically a map of variety in the sense, right? That it takes regular function to regular. That's how you define abstract variety. It takes the sheaf to the sheaf. The map from, so this is a map. So phi, this is a map from OY to f lower star of OY, right? OX. This is the map phi hash. That's how you define the abstract variety. Okay, so this is morphism of quasi-projective variety. Now the point is that so now it makes sense. What is that? So now you have AN. So now you have so now map, you had this AN map, which is you denoted by and this UI. This UI is a quasi-projective variety. So now you say that this is isomorphism, because AN is a affine variety, so it's a quasi-projective variety, right? So this is a map. This map is an isomorphism. Not only homeomorphism, but it takes regular functions to regular functions. Inverse morphism is also defined, right? That psi I inverse, yeah. That is the inverse map. So this is an isomorphism. We saw that homeomorphism does not mean isomorphism, but in this case it is an isomorphism, and that's a very important fact. So I leave this as exercise. Okay, try this as exercise. Show that this is a isomorphism. Okay, so now now the last thing which I will do, this is very important. I maybe not today, to next class, theorem. That Y is a projective variety in Pn. And Sy is a homogeneous coordinate ring. First is that now OY is a sheaf of regular functions on Y. So, but you take open set OYY, that is all regular functions on Y. So, this I denote it by sometime I will write OY. This is nothing but constant. This is very unlikely, right? This is very different from the affine case. At the affine case, it was the coordinate ring, but here it is. You have a coordinate ring SY, but it is not true. For the so this is a very important result. That projective variety, there are no global regular functions. So global function means you have a function from Y to K in your category. But in this case, other than constant, there is no function, and that's a drawback for projective variety, or the drawback or advantage in whichever you say. So there are not many functions defined over Y. So only the functions are defined. They are all monomorphic functions. That means those functions will, if you take any function of the form f by g, it will have some 0 on some g will vanish at some point of Y if it is not constant. If it is not a constant function, it is of the form f by g after every point, and that will have some 0. Yeah, globally. So global functions, there are no functions which. So this is very important. So this we'll do it in the next class, and also when you define regular function, you can talk about the stock. You know, that was when we defined stock, that has nothing to do with whether quasi projective or projective. You define only regular function, right? U comma f and v comma g, if they are equivalent. If you have a smaller subset of the u intersection v containing the point, that's how you define the stock. And you can talk about the stock. If OYP, then this is isomorphic. SY is a coordinate ring. Localize at MP and take the degree 0 part. So this is nothing but of the form f by g. I'll explain what is MP. F by g degree of f not equal to degree of f equal to degree of g, and g of p not 0. So MP is the maximal ideal, homogeneous. F and g are homogeneous. Or I should write capital F, that is better. And MP is a set of the ideal generated by homogeneous polynomial. Sorry. Ideal generated by f from f in SH such that f of p equal to 0. Homogeneous polynomial which vanishes at the point. Take the ideal generated by that. And this is a maximal ideal, and this is a homogeneous maximal ideal. And what is SYMP? You take the localization and take the degree 0 part. And this is anyway, we'll prove this when I prove, I will explain more carefully. And the last thing is that the function field. So when you define stock, you also define function field. What is function field of y? Right. Function field of ky is nothing but sy. You take the 0 ideal, take the degree 0 part of the 0 ideal, localization of the 0 at the 0 ideal. That is the function field of ky, isomorphic. Okay, so I will come to this when I prove this. I will explain more, and today I will stop here.